From peg legs to bionics, the evolution of prosthetics. There are almost 2 million people in the United States today who are living with a missing limb. That's about 1 in 200 people. The people you see in these pictures here are unique, not just because they're missing a limb, but more importantly, because they have adapted and are continuing to do what they love most. Whether it's high jumping or rock climbing, these people have managed to defy all of the adversity against them. Now for me, I can't imagine doing what these people do. Some people might say they have a disability, but if you think about it, about 100 years ago, having less than perfect vision was considered to be a disability. I bet you or someone you know wears glasses or contacts, but you don't consider them to be disabled. It's merely a condition, something that has to be adapted to, but they are still able to continue living a normal life and completing daily activities. That's what biomedical engineers work towards changing for people with missing limbs. They want to turn their situation from something discouraging and difficult to something that's just simply an adaptation. Biomedical engineers touch the lives of many people by creating prosthetic devices that are so lifelike that losing a limb is no longer a roadblock, it's simply a speed bump. Today, we are going to go over the evolution of prosthetics and how it's changed over time, and then the different problem-solving mechanisms that are used by engineers to develop new prosthetic devices. And then finally, the future of prosthetics, which is known as bionics. We are going to start with the evolution of prosthetics. Prosthetics can be dated back to as early as 300 BC. While these were able to solve the most pressing issues caused by missing limbs, such as balance or the ability to grab things, these prosthetics were unable to mimic normal human motion. Furthermore, they obviously look nothing like a normal human hand or leg. Most of the prosthetics from that era would most likely be associated with pirates, such as Captain Hook. On your right, you see a hand, and it's made out of iron or silver. But it was made in the 1500s during the European Renaissance. Because it is fully comprised of metal, it's really heavy. If you look close, you can actually see that there is a lever that the user can use to rotate the wrist and move the thumb so that the user could lock it in different positions before using it. Someone with this device would be able to grab things by using the levers, but it was hard to use because it didn't allow for small motions. This is one of the first prosthetics to actually look like a human appendage. On the left, you will see a pre-Civil War era prosthetic leg. This invention introduced the knee joint, but still had no ankle joint. This device was incredibly heavy and not lifelike at all. It was very hard to attach, and it wasn't user-friendly at all. Shortly before the Civil War, the Ainsley's leg was invented in Europe. It was the first non-locking below-the-knee prosthetic. The addition of the springs and an ankle joint and extra material to fully conceal the amputation allowed for this leg to simulate natural-looking movement. The Ainsley's leg remained one of the most advanced prosthetics in the field until World War II. At the end of the war, the US government made deals with military companies to focus on improving prosthetics rather than weapons. The incredible advancements made during this period have led to the prosthetics that we have today. Now, we are going to talk about the current prosthetics and the problems that engineers are trying to solve when building them. Biomedical engineers are working to make prosthetic devices more lifelike, which means that they're trying to use materials in the prosthetics that are similar to those in the human body. Biomedical engineers collaborate with material science engineers or chemical engineers to determine what materials are best to use, depending upon the application. If we're looking to design a leg that will be used for running, there are different properties that need to be taken into account. It needs to be strong so it doesn't break, flexible so it can be used to generate force, and it needs to be able to generate traction in order to be used for running. These considerations would be provided to the materials engineer, who would then decide what type of material would be best suitable for this application, and how best to shape that material, whether it is 3D printing, molding, etc. Next, biomedical engineers collaborate with mechanical engineers to analyze how different body parts move and how much force the bones within those limbs need to withstand. They then take this information and design joints out of metals and other materials to create prosthetics that are just as strong, if not stronger, than the body part that would have been there. Mechanical engineers will determine the forces that a prosthetic device will have to withstand by measuring how our joints interact during a gait analysis lab. They will have patients walk on force plates and analyze all the forces that are on the joints and be able to gather information from this. They measure the angle of the prosthetic and the forces on the plates and try to make the walking motion as lifelike as possible. Another problem that biomedical engineers must solve is communication. The nervous system, which runs all throughout your body, from your toes to your fingertips, transmits information in the forms of electrical signals. Biomedical engineers work with computer systems engineers to simulate the nervous system in prosthetic devices by using electrical wires to translate the information. Now that engineers have been able to create prosthetics that are easily able to mimic basic human motion, they're able to make advances that allow people with missing limbs to participate in physically intensive activities that they wouldn't have been able to before, such as running at a competitive level, ice skating, water skiing, or even racing in a Tough Mudder. This video is really incredible because if this man were to roll down his pant leg, you wouldn't even be able to tell that he is wearing a prosthetic limb. The movement and technique of his skiing is so natural. This is the ultimate goal of prosthetic devices, to completely restore someone's ability to do something that they love without other people knowing that some tragedy had occurred. The man that you see here is Professor Hugh Hare. Dr. Hare is a professor at MIT, and he lost both of his legs in a rock climbing accident. After the accident, Dr. Hare completed an enormous amount of research in biomechanics, and he actually designed and built the rock climbing legs that you see in this picture. The legs he is using on the right are actually so advanced that they can be controlled with an app on his phone. He can change the length of his legs by using the app, and this helps him rock climb or complete other difficult tasks. He also developed customizable legs based on what task he is completing, for example, running or walking or jumping. This leads us into our next section, which discusses the future of prosthetic devices and bionic limbs. The way that bionics is portrayed in the movies is robots and humans coming together. Well, the study of bionics is the study of mechanical systems that function like living organisms. So unlike the prosthetics we have been looking at before, bionics are not merely attached to your body, but now they are also communicating with your body. Computers are no longer just some box where we Google answers and go on Facebook, but now they're a physical part of people's lives. Bionics works by electrodes on the arm detecting and translating the nerve impulses sent from your brain to a specific muscle location. The electrodes then send that information to the arm to make it move in a certain way. In some very advanced bionics, the arm is actually able to send messages back to the brain, and that allows you to have a sense of touch once again. Computers are no longer cold, separate beings, but actually a part of life. The first step is when the doctor redirects the nerve to the patient's chest muscles. Then, when the patient thinks about a specific movement, the nerve impulses travel from the brain to a corresponding location on the muscle. Next, the electrodes on the harness of the arm will detect electrical impulses from the nerves and forward them to the arm. Finally, a computer processes the electrical impulses and makes the arm perform certain movements. And sensation nerves reroute to the chest skin, allowing her to feel once again. When engineers want to design a bionic limb, they must mimic the mechanism that goes on in our body. Our body sends messages, just like text messages, called action potentials. These action potentials are carried by nerve cells. So how do action potentials actually move your muscles? The action starts in your brain with the idea, and then it is transmitted from your brain down into your fingers with the electrical signals, which then stimulate the muscles to contract. And then the signal goes back up to the brain to confirm that you actually did wiggle your fingers. This signal moves at about 200 miles per hour. Action potentials are similar to a game of telephone. The nerve cell is charged, and then the charge changes from positive to negative, and then that change gets passed all the way down the cell. Action potentials are similar to a wave around a sports stadium. The way that the cells send messages through your body is the same way one person starts the wave, and the next thing you know, the wave is traveling around the entire stadium. Another really incredible advancement that has been made in bionics is fine motor movement. If you think about tying your shoes, it's a really simple activity. Most of us learn how to do it in elementary school, and we don't even think about it anymore. But for someone with perhaps only one hand, tying your shoes can be an incredibly insurmountable task. In this video, you can see that the bionic hand has actually been able to mimic the fine motor movements of the hand and can actually tie the shoe. For someone with a disability, such as a missing hand, being able to tie your own shoes can be a small but important victory. In the future, robotic and bionic arms won't need action potentials or to be connected to the nervous system in order to mimic human actions. It will be based off of muscle stimulation. As you can see, the hand on the right is interpreting the muscle movements of the arm on the left in order to mimic the motion associated with those specific movements. So if you wiggle your fingers while holding your forearm in the same way I am, you'll feel something in your forearm. Well, what is that? In the video, you see the sensors that are attached to the forearm. Those sensors pick up movement in your forearm and are able to translate that into hand movement. With only 4 sensors, the amount of movement that can be translated is limited to opening and closing your hand. In order to rotate your hand, you would need many more sensors. However, the man you saw in the previous slide with the model had only a few electrodes attached to his body. In order to receive every message that the nervous system is sending in order to power an entire arm, you would need all of the electrodes you see on this woman, and even more. To replace an entire arm, it would take an entire backpack's worth of sensors, which is seen in the next video. This is a problem engineers are trying to solve. How can we pick up the messages that the nervous system is sending without needing an electrode for every single motion? Clearly, there are a lot of flaws with the current system. The backpack is very heavy and is even causing her to lean to one side, which could lead to other negative effects on her health. In order to operate the arms, she is required to wear a big backpack, and the motions that you see her doing are not exactly lifelike. They are even jerky. Even her reactions appear to be somewhat delayed with the prosthetic arm because it is taking a longer time for the action potentials in her body to be translated into motions that would have been made with the arm. So even if biology isn't your favorite subject, and you think that you can't have an impact in this field, there are so many ways you can get involved. All different types of engineers are involved with prosthetics, including mechanical engineers who fine-tune the motion, computer science and electrical engineers who develop the interaction between the nervous system and the limb, convert electrical impulses, and finally, material science engineers who determine what materials to use for the prosthetic device. The field of prosthetics is a very interdisciplinary collaboration. There are many different fields all working together to reach a common goal: to help those with missing limbs do anything they want. The sky is the limit for them, And by pursuing a career in engineering, the sky is the limit for you too. So for the next portion of this presentation, we're going to go into the demonstration. And we're going to build prosthetic fingers. And we're going to do that by using household items such as masking tape, popsicle sticks, straws, rubber bands, and paper clips, and also scissors to use at your discretion. So the real point of this portion is to build a finger that's modeled after your own finger. So for example, the way your finger can bend at these two joints is really important. But if you try and bend your finger backwards, it doesn't actually work, and you can't actually push past a certain point. So these are all design characteristics that you have to think about when building your prosthetic finger. I like to start by using a popsicle stick because it's very rigid, and that's very similar to how the bones work in your finger. So I like to break mine apart into 3 separate portions to represent the 3 bones in your finger. Next, I like to think about the joints, and the joints can be modeled by using a straw. A straw is really good at bending in both directions, but that's not what your finger actually does. So that's something we'll have to come back to when we're refining our design. So I like to use tape to keep it all together because it holds it together really well, but also allows for a certain degree of movement. Taping can be a little tricky, but don't get frustrated. So this is one example of how I would build a joint with a bone and with bones and also joints. And see how it bends, but it's also able to bend backwards, which is not what we want. But before I tackle that design challenge, I'd like to build the second portion of my finger, which is the lower half. Once again, I use tape to hold it all together. What's really exciting about this particular design challenge and this demonstration is that there's no real right way to do it. It's really up to you and how you see that a finger should be modeled. So here I have both of my joints, very similar to a finger, but there's no real way to control them and there's no real way to stop them from going backwards. So now I'm going to show you a finished product. And this is something that one of the students who has done this demonstration has built before me. So what's really interesting here is you see that there's bending on that top joint, but also you can even get it to bend at the second joint. And you have complete control by using things such as string or rubber bands. And this kind of represents a tendon within your finger, which is really important. So this is one of the best fingers that has been built when doing this demonstration. And it's incredibly up to you what you see fit and when you're building your particular design. It's important to think about all the design considerations and really make sure that you're doing the best you can do when building your finger. Thank you for watching this presentation brought to you by the Engineering Ambassadors.